The topic of my speech today is predicting abalone age using machine learning. First, let's take a look at the case background. Abalone farming relies on manually counting shell rings to determine age, which is time-consuming and a costly process and difficult to scale. And limited scalability, sustainability risk, and high operational costs are the main problems. So accurate age prediction is crucial for sustainable harvesting and profitability. And our objective is to leverage machine learning models to predict abalone age based on physical attributes to enhance accuracy, lower costs, and optimize harvesting. And first, we should install necessary libraries for automated machine learning and visualization, classification, fetching data sets, and for EDA. And also in the code in this picture, we can see that we also install the libraries for data handling and visualization and numerical operations. And also sklearn library is installed for various machine learning functions, and XGBoost and LightGBM is installed for analyzing structured data. And before we analyze the data, we should pre-process it. We first load the abalone dataset from the UCI repository and stores it as pandas data frame form for subsequent data processing and model training. And we also use pd.concat function to merge the feature data X and the target variable Y into a complete data frame. An auto visualization class function performs automatic visual analysis, and auto visualization function classifies the data type by randomly sampling 2,000 rows of data and visualize the distribution and interrelationship of the variables. And let's have a look at the data set first. And we can see that for the X functions, we have sex, length, diameters, and other functions. And for the Y function, which is the dependent variable, we have the rings number, which represents the age of the abalone. And we also have some plots here, like scatter plots for these variables. And this plots, box plots, probability plots, and Boolean plots, heat map, and so on. And the second step for data pre-processing is examine the skewness. And the skewness of each X variables are firstly calculated to analyze the distribution pattern of the data. And why it is important? Because heavily skewed data may affect the performance of the machine learning model. So we should determine if data transformation is required, or we should identify outliers in advance. So Turkey's rule, you can see the code in the third picture here, which is also the IQR method, was used to detect and remove outliers in the rings, which is the target variable to improve the stability and predictive performance of the model. And in this case, this threshold is set as median plus or minus 2 IQRs. And we can see that for the X variables, which are the independent ones, the skewness of these variables are mostly fairly good, except for the height, it has a fairly high skewness. And for the rings, the skewness is 1.11. And after we remove the outliers, we can see from the box plot that there are no outliers anymore, and the data set is all good, and we can start analyzing it. And to analyze the data, the first step we should do is data set splitting. First, we split the data set into feature metrics X and target variables Y, which I mentioned before. And then we should split the data into training and test sets and maintain the same data proportions, which is 80% training set and 20% test sets, to ensure the model is evaluated on unseen data so that we can prevent overfitting, and the distribution of training and test data is similar for better model generalization. And in the code in the third picture, we can see that feature scaling is conducted using the normalization and standardization to ensure all features are on the same scale to prevent features with larger magnitudes from dominating the learning process. And next, we can conduct a random forest model to find out the feature importance. From the code in this picture, we can see that a random forest regressor model is trained to retrieve the importance score of each feature to indicate how much each feature contributes to the model's predictor, which is the rings number. And why it is important? Because feature importance helps us identify the most significant predictors for rings, and it can also be used for feature selection, reducing dimensionality, and improving model performance. And from the bar chart below, we can see that shell weight is the most important feature, and shuft weight is also a strong predictor, and sex has the least impact on rings. And let's talk about how random forest model is suitable for the data set. First of all, the relationship between the input X features and abalone age, which is represented by the Y variable rings, is likely nonlinear, and the random forest can capture these relationships well. And the second one is that the random forest model can provide insight into which feature contributes most to the age prediction, which is shell weight I mentioned above. And also it is robust to noise and outliers and works well with the moderate size data set in this case. And next, let's move on to model evaluation for the base learners. First, we define two functions. The first one is performance function, which evaluates model performance using MSE, MAE, and R squared. And we assume a good regression model should have small MSE and MAE, and R squared should be close to 1. And the second function is the predictors vs actuals functions, which plots a scatter plot comparing actual values to predict values. And if the predictions were perfect, we expect all points would align along y equals to x diagonals. And these two functions can test how well each model explains the actual test data set. And then let's train and evaluate these models. We run multiple regression models, which are the base learners, including linear regression, lasso, ridge, elastinet, and so on. And also in the code in the second picture, we perform the performance metrics are printed for each models, and scatter plots are generated comparing actual and predicted values. And let's take a look at the outputs. And from the output of these regression models, we can see that linear regression and ridge regression models performs the best, and KNN regression showed comparable performance as well. And SVR captures some nonlinear but had higher arrow. And while decision tree and elastic net showed overfitting, and lasso and MLPs are the ones that performs the worst. And I also rank these models by the indicators from the best performance model to the worst performance model. And now let's talk about how random forest balances bias and variance by 3 ways. The first one is reduce variance with bootstrapping. The second one, reduce overfitting with feature randomization, and also maintaining low bias with deep trees, not a single tree. And we can see that the random forest model is better than those models in the left picture, which I mentioned before, by many ways. For example, it's better than linear models because it captures non-linear relationship, better than single decision tree because it prevents overfitting, and better than KNN and SVR model because it's scalable and it's more stable than neural networks as well. So among all these models, we can see that random forest model can balance bias and variance most. And last, let's talk about the implications for real-world applications. First of all, we can say that machine learning can provide a scalable solutions. While traditional age determination methods are time-consuming, machine learning can offer a faster and data-driven alternative. And also its potential for further feature engineering, and it can avoid overfitting and ensure model interpretability. And for policy and business applications, both governments, fishers, and farms can benefit from it. And that's all for my speech today. Thank you.